Meters, meters, meters. They're everywhere around us, measuring all sorts of things. A very great many of them measure the strength of electric currents. These meters are called ammeters because they're calibrated in units called amperes. By now you know that electric current is just the flow or motion of elementary charges. The natural unit, then, in which to measure this current is just the number of elementary charges which pass any given point in the circuit during each second. Now, how many elementary charges per second is in an ampere? A single elementary charge is too small a unit to be used conveniently in measuring electric currents. So we use a package which contains 6.25 times 10 to the 18th elementary charges. We call this package 1 coulomb. You'll see a little later in the study of electricity just why we choose a package this size, a unit this size. Now the flow of this many elementary charges per second we call 1 ampere. Here we have a simple electric circuit, a battery, a variable resistor so that I can change the current, and a small bulb. Let me connect them together. And I'll adjust the variable resistor so that the bulb is about that bright. Now to measure the current flowing in this circuit, I'll insert an ammeter. Now it doesn't make any difference where in this series circuit I insert the ammeter because the current is the same everywhere. The meter indicates a current of about 1 ampere. Now this brings us to an important question. How can we be sure that this meter is accurate? If the manufacturer had one accurate meter, he could calibrate all the other ones he produces from it. But how do you calibrate that first meter? One way to calibrate it is to put it into a circuit where you can count by a foolproof method the actual number of elementary charges flowing past any point in the circuit per second. It is possible to get a direct indication of the number of elementary charges flowing in a current by doing an electrolysis experiment, the type usually called a Faraday experiment. You have probably all done an electrolysis experiment like this one. The water has been made conducting by adding a little salt. I'll connect the batteries, and you see that the water decomposes. Hydrogen bubbles up at the negative electrode on the right, and oxygen bubbles up at the positive electrode on the left. If I let the current that I'm using here flow for 10 minutes, I collect this much gas. After the bubbles settle down, I can measure the volume of the gas I've collected. So from Avogadro's law, I can determine the number of molecules of gas, either of hydrogen or of oxygen. Now you probably recognize this figure. It's Avogadro's number. Under normal conditions, 22.4 liters of any gas contains 6.025 times 10 to the 23rd molecules of that gas. For easy figuring, let's round this number off to 6 times 10 to the 23rd. Many experiments have shown that there are 2 hydrogen atoms in each hydrogen molecule, so that in 22.4 liters of hydrogen gas, there are 12 times 10 to the 23rd atoms of hydrogen. Now in just a moment, I'm going to do an experiment where I'll collect 22.4 cubic millimeters of hydrogen gas, 1/1,000,000th of this value. That volume should contain 12 times 10 to the 17th atoms of hydrogen. So that I'll be collecting 12 times 10 to the 17th atoms of hydrogen in a volume of 22.4 cubic millimeters. This is the equipment with which I'll do the quantitative electrolysis experiment. This battery is connected through these wires to a pair of electrodes in this beaker. The water has been made conducting just as in the previous experiment. The electrodes are very fine platinum wires positioned beneath two small tubes. When I connect the electrodes to a battery, hydrogen bubbles off the wire on the right, oxygen off the wire on the left. You can see the gas collecting in the tubes and displacing the water. Between the two tubes, you can see thin black lines drawn on a white background. These lines mark off lengths of tubing which have a volume of about 22.4 cubic millimeters. Now I'll disconnect the battery and release the gas. Here is a meter. It's a fairly sensitive meter, and I've covered the numbers on the face so that the face is blank. Now I want to calibrate one point on this meter when it's in the circuit in terms of the actual number of elementary charges flowing through the circuit per second. I'll connect it in series with this circuit now. And I'm going to allow the current to flow until I've collected 22.4 cubic millimeters of hydrogen here, which you will remember is 12 times 10 to the 17th atoms of hydrogen. Now it's important to know that there are just as many elementary charges flowing in the circuit as there are atoms of hydrogen coming off at the negative electrode. Let me illustrate that with a drawing on the board. Let these represent the electrodes, and this the battery. This is the positive electrode, and this the negative electrode. Hydrogen ions in solution have a positive charge and are attracted to the negative electrode, where they pick up a negative charge and go off as a hydrogen atom. While this is going on, oxygen ions in solution are giving up their negative charge to this terminal, thus making available free negative charge to the circuit here. For each free negative charge placed at this point, the battery makes available a negative charge here for combination with the hydrogen ion in solution. So that each hydrogen atom which comes off at this point, it represents the flow of one elementary charge around the circuit. If we count, say, 3 hydrogen atoms coming off here per second, and have a meter in the circuit over here, the meter will point to a position which represents the flow of 3 elementary charges per second through the circuit. Now we can't count this small a number, so if you'll remember, we're going to count 12 times 10 to the 17th atoms of hydrogen coming off at the negative electrode in some given interval of time. Now I'll need a timer in this experiment, and I'll use this stopwatch. I'll mark the position on this meter where the needle comes to rest. Now let me mark the 0 position. Since it'll take a little while to collect this bubble of gas, I'll be turning on the stopwatch at the same time I connect the battery. I'll then turn them both off when it seems to me that the bubble of gas is down to this first black line. Now I guess we're ready to go. This current causes the needle to stop at this point. You can see the hydrogen collecting in the right-hand tube. When it reaches the first black line, I'll shut off the current and the timer. There. That was about 20 seconds. So now let's organize our information here. We actually counted 12 times 10 to the 17th atoms of hydrogen in 20 seconds. So that we counted 6 times 10 to the 16th atoms per second. Each atom represented the flow of one elementary charge through the circuit, so that we actually were counting a flow of 6 times 10 to the 16th elementary charges per second. Now you remember that 1 ampere is equal to 6.25 times 10 to the 18th elementary charges per second. And we counted 6 times 10 to the 16th elementary charges per second, which is a ratio of about 1.04 times 10 squared over 1, or just about 100 to 1. So we had a current of about 0.01 100th of an ampere. So in this experiment, we had a flow of current of 100th of an ampere, 10 milliamperes, measured directly by counting the number of elementary charges flowing. Now let's take a look at this meter. This mark represents 100th of an ampere, or 10 milliamperes. Now if I connect the battery again, we see that the pointer points to the mark, which represents 10 milliamperes. Now if I uncover the face to show the factory markings, you can see that the 10 milliampere division falls where we made our mark. We can assume our experiment was quite accurate, and thus can say the meter is, in fact, well calibrated. By counting atoms of hydrogen in this experiment, we got a direct one-to-one count of the number of elementary charges flowing through this circuit. We were dealing with basic units of charge when we calibrated this meter. Later, more evidence will show that these elementary charges involved in the electrolysis experiment are the same elementary charges which are in the Millikan experiment. Now we were using a rather small current here, 10 milliamperes, and collected a small volume of gas. But still we were dealing with a large number of atoms per second. 60 million billion elementary charges per second. This amount of current was a fairly steady current. The needle on the meter didn't fluctuate much. But suppose I could count only 60 elementary charges per second. This counter is measuring a current of even less than 60 elementary charges per second. In fact, it's measuring less than 20. It clicks once for every second electron because of the design of the circuit to which it's connected. To measure currents this small accurately is a bit tricky. I'm standing beside the apparatus devised to do this. It was designed by Mr. Madsen here. Borg, could you turn it off for now? To better understand what we're going to do here, let's take a look at the various pieces of apparatus. This meter can be used as a very sensitive ammeter. It has been accurately calibrated by the manufacturer. If I set the rain switch on the meter to its most sensitive position, the meter will indicate a current of 10 to the minus 11 amperes at full-scale deflection of the needle. In other words, when the needle points here to 10. Naturally then, a reading of only 1, a tenth of full-scale reading, would indicate a current of 1 times 10 to the minus 12 amperes. But if we want to measure just a few elementary charges flowing per second, then we must extend the range of this meter. This tube is an electron multiplier. Let me take off the light shield so that we can see the interesting part. With the tube, we'll extend the range of this meter by a factor of 1,000,000. Let me show you something about the details of this tube. In this close-up, you see the fully assembled tube. In order to take a better look at how this tube operates, we'll remove some of the supporting wires and the resistors. These are the plates of the tube. We call them diodes. They are connected to a battery in such a way that each plate is more and more positive, going from right to left as you look at it here. The filament is located here. The filament is heated, and some of the electrons which boil off of it pass through a small hole in a shield. The electrons are accelerated to the first dynode. The diodes are especially treated so that when an electron hits a dynode, it knocks a few more electrons out of it. Each of these electrons is then accelerated to the next dynode, and each of these electrons in turn knocks out some more from that dynode, and so on through to the last stage. We can adjust the batteries so that for each electron that goes to the first dynode, there are just about 1,000,000 coming out of the last stage and being collected on the output wire. By connecting an ammeter into the circuit at the output stage, we can measure the amplified current. To adjust our tube for a gain of 1,000,000, we will have to compare the output current with the current from the electron gun alone. We disconnect all the diodes except the first one. Then, putting an ammeter into the circuit from the first dynode, we measure just the current of the electron gun. We've compared the measurement of the electron gun current with its amplified current from the final output of the multiplier, and have adjusted the batteries so that for each electron coming from the gun, we get a burst of 1,000,000 from this final output stage of the multiplier. Having actually done the calibration, we're ready to use the tube. Mr. Madsen's going to turn on the filament and adjust the current so that it is very weak when it flows through the electron gun. This meter is connected directly to the electron gun, and the multiplier is not in the circuit. We'll read the current on the meter now. As you remember, when the needle is at 1, the current is 1 times 10 to the minus 12 amperes. You'll notice the needle holds pretty steady about this point. He doesn't have any trouble measuring a current this size. Let's try a smaller one. Mr. Madsen is going to change the connection so the multiplier is now in the circuit. Then he's going to adjust the current from the electron gun so that it is only 1 times 10 to the minus 17 amperes. He can't check this current directly on the ammeter. The meter isn't that sensitive. But he knows when he's got it because the output current, which he can measure, is just 1,000,000 times as large, or 1 times 10 to the minus 11 amperes. We'll adjust the meter so that when we have this output current, the needle will point to 1. The meter will, in effect, then be responding to the electron gun current of 1 times 10 to the minus 17 amperes, which is 60 elementary charges per second. Now let's see. The meter is set, and Borg will change the current from the electron gun. The needle is moving. There it is, pointing just about at 1. We really can measure this very weak current of about 60 elementary charges per second. But the needle won't hold still. It fluctuates back and forth on both sides of 1. This fluctuation, which isn't noticeable in larger currents, illustrates a basic fact about all electric currents. The elementary charges that make up a current don't go through the circuit with perfect regularity. In this case, there are sometimes more than 60 per second, sometimes less. The exact moment at which any charge goes by is just a question of probability. Let's see if we can make this more evident in several other ways. First of all, you can hear it. You hear the amplified sound of the elementary charges in this very weak current. Now I'll make the current even weaker. Now the rate is between 15 and 20 per second. Secondly, we can see a visual trace of each elementary charge if we display them on the oscilloscope tube face.
The large pulses you see are made by amplifying each electron in this weak current. The narrow line below them comes from other parts of the circuit and the oscilloscope, and not the output of the multiplier tube. If I cover up the narrow line, I think you can see that the pulses made by the electrons in our current don't make a perfectly spaced pattern on the tube, but appear at random intervals across the screen, just the way the electrons pass randomly through the circuit.
If we use this equipment, we can actually count the number of elementary charges which constitute this very weak electrical current.
And in fact, by using this method of directly counting elementary charges, we can calibrate that same ammeter which we used earlier. And we get exactly the same results as we got by doing it by electrolysis. From this, you should recognize that it is really the average number of charges that pass per second which designates the strength of an electric current, whether it be in this small current or the larger currents we measured earlier by electrolysis.